Okay, is that working? All right, great. Well, thank you, Mohammed, for a nice introduction. Thank you for inviting me. I mean, I'm really honored to be here. I have not been doing that much work in visualization, to be honest, lately. So I sort of feel like this is a special treat. But visualization is actually probably the subject that I think about the most. And I sort of have an oddball talk here. I hope you can get something out of it. It's about notation, and it actually. A bit of background. So I gave a keynote at Eurovis once before in 2009, ancient history. Most of you were probably born then, but maybe there were some that weren't. Did anybody see that keynote, by the way? Is anybody in the audience? Oh, a few, okay. So this is what I've been thinking about since then. And that was probably one of my favorite talks I've ever put together. Basically, the point of that talk, just to summarize, and I'll include some of it in here, some of the slides, because I'm sure most of you were there, and you won't remember, most of you weren't there. But the idea of that talk was that there's different ways of solving problems. We have different tools that we create. We have language, write paper, talk, we learn about logic reasoning, how to do proofs. We have mathematics, and we have all these concepts in mathematics that goes into geometry, which we use all the time. Then, a fairly maybe a little more recent, but a fairly big thing nowadays is probabilistic reasoning, statistics, and AI, machine learning, probabilistic reasoning. There's a lot of thought about computational thinking around 2009. That's a buzzword, like how to teach people about computational thinking. And of course, we're all in visualization, and at Stanford, we actually have a fairly big course on visual thinking. And I claim these are sort of like different ways of approaching problems. You could just use visualizations, or you could do mathematics. And the point of this talk was that these all have sort of advantages and disadvantages. And part of an educated person is to be able to use them through, to switch back and forth, to know which one to use for what kind of problem, and so on. So that's a very ambitious talk. But it's sort of, I'm a professor. I'm an educator. I teach people. If you ask me what I do, I teach people how to think. They come to Stanford, and my job is to teach them how to think. So, that's something I'm interested in to see. I like to connect these things up. Like, I don't like to just use visualization. I like to use visualization and other things at the same time. I think we all do. But sometimes we're not aware of it, and we don't make conscious decisions about what's the best way to approach the problem. So anyway, I don't think that talk is online or anything, but it's a fun talk. Okay. Then another thing I've always been really interested in is language and graphics. So when I got into visualization, I worked with visual cognition. Professor in psychology at Stanford, and she got me onto this language and graphics on day one. And her expertise is how to perform abstraction. She studied maps, diagrams, and things like that. If you look at these sort of abstract forms of imagery, okay, and statistical graphics might also be like that, or often they're very much like a step towards language. You have the real world, an image of the real world, a photograph, and then you try to abstract it like a map. Well, it's sort of one way to think of what you're going to put on a map is what do we tell people about, and then what happens is when people look at the map, you can ask them like what information they got, like what's this telling you, what's been communicated by this thing. And so there's this transition sort of into your brain. Now you can argue whether your brain works in language and so on, kind of leads. But there's this leap into this sort of like more symbolic world. And a lot of visualizations, they have to make that leap, right? In order for us to reason about them, they have to make that leap. So she did a lot of work in language and graphics, and I was always very inspired by that and helped me think about abstraction. And even at Tableau, one of the first things I did at Tableau, I wrote the first version of Tableau with my student Chris Stolke. And one of the things I did was write a caption generator. If anybody's ever used that feature. But the motivation for that is if you look at a picture, there's some context, like how was the picture created? Like what database did you use? Filter it, you know, were you part of some process? And so you needed all this context as well, and that wasn't in the picture itself. So if somebody just copied the picture and put it in the paper, it'd be unintelligible to somebody who just wasn't aware of the context. They weren't the animals that made the picture. And so, you know, I wrote a caption generator that would fill in all this context. And then I was providing the NLP interface effort at Tableau as well with the others. But the idea was, you know, back to this idea of language and grammar. Okay, then Tableau itself, if you know the history of that, it was based on Bertin's semiology of graphics. So semiology about symbols, and the grammar of graphics by Lee Wilkinson, which is sort of like a language-like approach for specifying and generating graphics. And I mean, I'm not going to spend a lot of time on AI, but obviously, you know, obviously language and imagery is a huge topic, right? It's so remarkable what you can do with stable diffusion and LLM. I was just playing around Google's Veo thing. You know, it's just amazing, right? You just type in some text, type in a story, and it'll generate all this imagery. So there's obviously some deep, like, how do they do that? And it just seems like some two worlds that are like separate, but they aren't separate, right? So this is a really big theme of a lot of my work with is language. Finally, what I do in a lot of my other projects is what I would call domain-specific languages. So Tableau is based on a domain-specific language. HQL. At Pixar, I worked on a render-time shaping language, which is a domain-specific language. I worked on real-time shaping language, GLSL. Some of our students did this system called CG, you may have heard of it. It's sort of secret now. You know, there's lots of other domain-specific things. I can give lots of examples of other ones I've worked on. But they're pretty widely used. MATLAB, Python, SQL. You know, they're all languages that are sort of more specialized than, say, C. Right? And I've always been fascinated with them because, you know, you're trying to raise the level of abstraction when people do their work. And so you come up with these objects that have a useful semantics. Like PyTorch is based on principles. And SQL is based on relational algebra sets. And they have some optimized syntax, right? It's a lot easier to type in things that sort of look like math for matrices than it is to just type C program with loops, right? You just have these higher level things. And so, you know, how do you build systems that, you know, are higher level and have new abstraction? So that's the context of the talk. So a lot of this was in that other talk. But anyways, one thing I'm interested in is if you do languages and stuff, one of the first things you hear people say is it's about semantics, not syntax. Anybody remember heard that quote before? That got drummed into me when I was in grad school. When I first got, you know, it's not about the syntax. All these languages have different syntax. Ignore all that. What's the semantics? And mostly what I would do at Tableau is tell people it's about the semantics, not the visualization. It's like, what does the visualization represent? You know, and what does that mean to the people? What's the meaning of it? You know, what are people going to say about it? What do they want to reason about it? You know, the visualization is just a bunch of symbols, a bunch of forms. So anyways, I was a super big fan of using semantics. I'll get back to that. On the other hand, being a visualization person, I really like the syntax. Like I have very strong opinions about programming languages and math notation and visualization, and I think they're really important that the syntax is there. So it's like about both. You know, you have the semantics of the domain, and you have the notation, the visualization, and the concrete representation of the domain. So I did a lot of work in programming languages recently, and I would hang out with all these programming languages, and they just constantly say it, semantics, not syntax, semantics, not syntax. And they say they don't care about, you know, syntax. And yet they spend all their time, you know, working on the syntax to make it look really nice. So it's sort of funny, but they don't know why. They poo-poo it, they think it's unimportant. Now as a visualization person, I think it's really important. So let me give you an example of, like, you know, how people get confused about what's important. Okay, tensors, hot topic. You know, you have the TensorFlow, tensor processing units, tensor cores, you know, deep learning. all based on tensors. Okay, so I like to talk to people about tensors. Okay, so the first thing you ask somebody is, do you know what the Einstein summation notation is? Actually, I'll ask, how many people know what that is? Yeah, pretty quite well over half, right? I actually went back and looked up this paper, okay? And it's in the paper on the foundation of general relativity. Actually, he wrote about, sort of interesting, he wrote about 6 papers on this subject. And each one, the first few were sort of not quite there, like graphs. And then the 6th paper sort of came together. And he figured out a really good way of like writing down all the math and having all the principles. And in this paper, he introduced this notation. Because like once he'd figured it all out, he wanted to communicate it to people and be able to really clearly state, you know. And if you know about general relativity, the idea is that space-time is sort of curved. So you have this metric tensor that describes the curvature. So a lot of the physics is about, what is the curvature of space-time. Anyway, you can read this. By the way, this paper is very readable. You can just read this paper and pretty much understand it. I mean, it looks a little gobbly. But he says that there are these tensors, and these are these multilinear things, that have multiple indices. The number of indices is called the range. And then there are 2 kinds of indices. These ones that are subscripts, which are called covariant indices, and ones that are superscripts, which are called contrarian indices. It's possible to do this thing called contraction, and he introduces notation where if you repeat the same symbol, in this case mu in the first example, then that's equivalent to a summation over mu, which he's showing in this equation. And you can do this multiple times if you want. And that's it. It's just notation. You could have wrote the summation and multiply type of thing. But smart guy. So he invented this notation to help him communicate the theory of general relativity. He thought this was really quite cool. He was very proud of it. Okay. Now you ask somebody, what is a tensor? Okay. All right. Who knows what a tensor is? Okay. All right. All right. I bet you all have some concept of a tensor. Okay. I bet it's not the right one. Okay, so here's what a tensor is. I was a physicist, so I know this. Okay. So first of all, everybody knows what a vector space is, right? You have this thing, you have vectors, you can add them, subtract them, scalar multiplication. These are and all problems. So what a mathematician will do is define something. As they'll say, there's some set of things, right? Set of vectors. There's some operations on those vectors, like addition. But the most important thing is to obey a bunch of laws. Right? And that's what we mean by the semantics. And to a mathematician, the fact that all these laws are obeyed is what gives it its semantics. So if you have a set like this in an operation and all these properties are true, then it's a vector. Okay? That's sort of basic stuff. Okay, here's what a tensor is. A tensor is a higher dimensional vector space formed from 2 vector spaces using a product. So you take like 2 one-dimensional things and make a 2-dimensional thing, and that's still a vector space. But it has to have this additional laws. That scalar multiplication acts a little bit funny. I'm not going to go into that. All right, how many people really give you that answer? So, I mean, I've talked to like every machine learning person, and by the way, there's a whole books that thick written on tensors. It's like not like a obscure concept in mathematics. So I'm not trying to criticize anybody, but most people don't know about the semantics. They don't know what these things are. They don't know what you don't know what operations you can do on them. You don't know what the properties of those operations are. But you know the notation, And so that's why I always say that a lot of people just think they know something because they know the notation. They know the syntax, but they don't actually understand the semantics. That's why the semantics is so important, because the notation should reflect the semantics. Einstein didn't know what a tensor is. So there's just this two-way street, Obviously the notation is really important because that's what everybody actually knows. And that's how we think with this notation. But in reality, there's this deeper structure, which is the semantics. Okay. So I'm going on and on about this. Okay, here's another interesting thing. By the way, these are fairly famous physicists. Penrose diagram. So So this was Penrose's PhD thesis. Fairly famous guy. Works in cosmology. You don't know him. Won the Nobel Prize, and he invented these things called Penrose diagrams. And he came up with this diagrammatic notation for tensors. So this, let me just sort of explain it to you, sort of cool. It's totally equivalent to this mathematical thing I was telling you. So, you have these tensors, and you can think of tensors as little boxes where there's inputs coming in on the bottom and outputs going out the top. So the indices on the top are the outputs, and the indices on the bottom are the inputs. And if you put two of these things side by side, like horizontally, that's like forming that product. So you form something that's a combination of the two indices. And if you connect them up top to bottom, that forms a contraction. Because you eliminate an index by some. Okay. And then there's one other trick you can do. You can loop the thing around and form a cycle. This is sort of like a recursive kind of thing. And so you can have these loops in it. And given this diagrammatic notation, you can form any tensor expression. Okay. And physicists use this all the time. It's quite famous for those. And anyway, it's just sort of neat. Like he invented this notation, and to him, when he was doing his work, on black holes and things like that, he found this a much more efficient way of doing math than using a bunch of sums and indices. And he found the properties. And if you look at these diagrams, there might be a bunch of properties about tensors you really never thought about, right? Like there's these loops in it, that they're recursive. And what's interesting about these diagrams is they can be generalized to not just tensors, but all sorts of other things that are graphical, diagrammatic things, like circuits, all sorts of things, process, flow graphs, etc. And these things are formally, well specified. So it's sort of interesting. There's lots of different graphical notions out there with visual programming environments. So most of them are very clearly specified. But this tensor stuff and these diagrams is very precisely specified. So it's sort of interesting graphical language to have in your back pocket. So anyway, that's another cool notation. By the way, some people will say, well, this isn't visualization, But, don't you see the beauty of these equivalences here? Right? And also, even the math, math is 2D. There's subscripts, superscripts, fractions, brackets, expanding brackets. It's very 2D. I have some great examples I can show you on my laptop. I like these giant mathematical expressions, which are giant 2D things. So, they're visual. And my definition of visualization is if it's on paper and you see it, it's a visual thing. So you have these different kinds of languages, say, and they have a semantics and a sense. There's also the pragmatics, but I'm not going to talk about that. But there's the semantics, which you can say there are these different things you're manipulating, these sets of things. You have these functions on those sets of things which were built in, and then you have these laws that they have. I tend to like mathematical specification, so that's what I'm calling semantics. Now, you can argue about that, whether that's the only definition of semantics, but that's a good one in computing. Then you have the syntax, which is like a concrete notation. So you have to write down, you have to somehow define, somehow represent on paper what you're talking about. And in computer science, we also talk about abstract syntax. So there's the Penrose diagram and the Einstein notation. Those would each be concrete notation, but they can both be sort of abstracted in some kind of abstract syntax because they're basically built on the same primitives, they just have different sort of physical realization. So that's useful in computer science. And then in computer science, if we have a language, often what we do is we translate, we have some evaluator, which translates from abstract syntax previously to semantics, to value. So we have an expression, we have a tree, expression, evaluate it, and a number. Okay, I know this is, but hopefully the point will become clearer and clearer. But these are really important concepts that really are helpful in visualization. Okay, so now this part This will just be easy go, because this is like Viz 101, okay? So the thing that was the hardest thing to do at Tableau at the time was convincing people that visualization was useful. And so these slides were the ones I came up with, which I would show the CIO. And I know you all know them, but I just want to show you. These actually work. You can take a total skeptic that doesn't think visualization is worth anything and show him these sites, and they'll believe it's worth something, okay? So first part of this is the slide I don't show. But, one of the big ideas, in systems of thought, is you have different representations of things, and different representations do things more efficiently than other representations. So this is like computer science 101, right? Data structures and counts. Remember that for us. And the example I always like is set representation. So, if you have a set, and by the way, this isn't common in database. You have different representations of sets. You can have a list, right? A sorted list, hash table, bit vector, binary. And then on sets, there are basically two fundamental operations. Take the union of sets and find an element of the set. Like, is this a member of that set? And the union is complicated because sets, by definition, you can't have duplicated elements, right? So you have to check for duplicates. When you take the union of two sets, you just can't concatenate the list because you might have duplicates. Now you can have multi-sets, but if you want to have a real set. So that means if you have a list, it takes order n squared operations to do a union and order n operations to do the find. Now, if you have a sorted list, you can do the union more efficiently in order n operation, and you can do the find in order log n log n. Okay, but union, I assume everybody can understand why that's true. I've done that algorithm, and then in general, the union is more complicated to find, but there are different ways. But then we get to this thing called a binary tree, where the union is actually really fast. It's faster than the find. And so here you have an example where one is better at one thing than the other thing, and the other one is better at the opposite thing. And there was this famous algorithm called union find by Tarjan, which showed that you could do the same thing with the same cost. Very complicated. But this is like, I guess we did this hammering by that in science that different representations support different algorithms, different efficiencies, and that's like one of the breakthroughs. I don't know if actually identified that in computer science. I think it went in ProList, Alan Newell, somewhere like that. But they just came up, they articulated this principle, that the representation matters and algorithms cost depends on representation. So the same thing applies to visual representations, right? And here's what my picture shows. There's perceptual cost, and so I always show tables for that. But how much mint tea was sold in the West? Well, that's like a lookup function. It's very efficiently performed in a table, but you need to have the headers done properly. And you use exactly the same tricks as you do in computing, right? You sort the things or you build a tree. And you can show that, sort of in log n time, you can find what you're looking for in log n time. And, so tables are really useful, like people who do tables, but if you're doing a lookup, they're about as optimal as you can get, right? And so, by the way, at Tableau, we probably spend more time on our tables than any other visual representation. They're just, the details are really, really important, and people use them all the time. So anyways, so that works really well. Great representation for tables. But if you change the question to what product in what region sold the most, right, you want to find the maximum. Now instead of like log n, it takes linear time. You have to scan through the entire table, okay? And actually, I think it takes order n squared or more time, because you start scanning through it and you forget what the maximum is. And by the way, if you have a skeptic, you just show them this, and you also bring a table with that table, okay? And they just will never, they will never find the max. You know what I mean? So you can, and you can, if you know what the cost structures of these things are, you can design examples that just make it overwhelmingly clear that the right visualization will make you more efficient at doing whatever your task is. But two different tasks, same representation, right? So I just found this like a really simple way of explaining this basic idea. But this is sort of, and then the question is, how do you do this? Well, you switch to a bar chart, and the biggest thing is something we can detect pretty attentively, and that takes constant. So you have this giant table. You show them that they were still working on trying to find the max, and then you pop up the bar chart, and they instantly find the max. And that's the end of that story. Okay. So you can, if you understand the cost structure. So Barbara just hammered this in. You have to think through what they're doing, and what the visualizations, what the cost structure of the visualization is, in order to design good visualization. I just think there should be more of this kind of visual analysis of the visualization, not visual analysis, where you have to write down the cost structure. And the cost structures are like mostly search. Mostly the people are looking for information in visualization, and so they have to search for it. There's also other ones like finding patterns and a few other key cost structures. But you can, once you sort of identify, how to map, some question into some visual algorithm that you often search for something, then you can figure it out. And if you, like you build a giant graph, like a giant airplane, you have to find a node that represents San Francisco. How do you find that? You wander, you're just looking everywhere, they all look the same, they all cover each other up. You just can't find it. You can't find the information you want. So you just have to identify, you just have to, it's more than just sort of that shows X. You have to say, given this task, what's the algorithm the person is going to employ to find it? Okay, so that's the easy one. Somebody said yesterday, oh, we should be studying the perceptual stuff anymore, and I sort of largely agree. I think once you get good at that, you can figure it out pretty quickly. And there are definitely things we don't know. But to me, the more interesting one was the cognitive construct. And my favorite paper here, which I always show, is the one by Zhang and Norman on representation of numbers, which is sort of interesting because I'm talking about notation. But everybody knows this paper too, so I'm not going to spend a lot of time on it, but they basically said there are all these different ways people have come up with representing numbers, like Roman numerals and so on, Arabic numerals. They have a little table of different ways of doing it, and they show all these examples of different civilizations have developed, and they analyze the cost structure of doing various tasks, like counting, tallying. Actually, a big fan of tallying is two people. He's tallying all the time. Adding Roman numerals is like a merge sort. You just, if you remember that, you just merge the two lists together, and then you pull less things that are the same, so you get 5i for the b. So it's like a merge sort. So you can figure out what the cost of that algorithm is. Okay. And these are symbol manipulations. But the real cool thing they came up with is I remember learning how to multiply different Roman numerals. Did anybody ever learn how to do that? I don't think that's a commonly taught thing. It's not a very easy thing to do. Okay, multiplying Roman numerals. Okay, you can go look up the algorithm. You'll be glad you weren't taught it because you never used it. Okay? But what they did is they analyzed the cost structure of doing multiplication. So this example is in the book on information visualization, multiplying these numbers together. But that involves a sequence of steps. So I would call that cognitive. It's a sequence of steps you have to do, to reason through this thing. You have to do this thing and then that thing, and based on the results of that, you have to do this thing. And they said, well, here's the algorithm. You have to know the position determines the power of the base, and et cetera, et cetera, et cetera. And then what they did is they said, what parts are you? The other really amazing thing about this paper is it's about distributed cognition. Like, what do you do in your head, and what do you do on the paper, right? And so they said, what are you doing in your head, and what are you offloading to the paper? Okay, and whenever you offload something to the paper, you make it easier. so, again, everybody knows this, but this analysis said it's obviously much easier to multiply handwritten equals together for a person than it is for a woman. And so you can take these tasks that are more of reasoning tasks, and you can apply these cognitive correspondence to those, and those are sort of more interesting than than the purely perceptual ones. And there's much less known about that. It's harder. Like the formula for doing that is not as easy to write down. It is for something like this, but in general, it's harder to do. And that's often what people are doing with these visual analytic systems is using them to reason through some problem. A good example is maps. I've done a bunch of eye tracking studies where people are doing maps. And it's really quite interesting. You sort of try to figure out, people use eye tracking to try to figure out how people analyze the problem. You find this information, you find this information, and to make some conclusion, you'll find this information. So, and you can measure if you look at some of these people, how hard they think, called cognitive load. And so you can actually figure out like when they're doing this thing, when are they thinking, act hard, when aren't these experiments are a little tricky, but you can often get really useful information. And then you can build a model. Okay, so this is like visualization 101, but this is well understood. So this just boils down like why visualization are really important. So let's talk about the first visualization. Okay, so now getting more onto my topic. Okay, I stole this title from this paper by Kenneth Iverson called Notation as a Tool for Thought. So he won the Turing Award a long time ago, and this was his Turing Award address, which is one of my favorite papers. Notation as a Tool for Thought. So you can see why I like it, like having given a talk called Systems of Thought, right? It's like, I have to give this thought, which is notation as a tool for thought. So Iverson was an interesting guy. So he, early pioneer in computing in the 60s. He was a Canadian. He lived in Alberta, which is in farmland, Canada, up north. And he lived in a small farmhouse and went to a school, a small school. And he mostly taught himself mathematics. Because he was no way of teaching mathematics. So he sort of rediscovered mathematics. Just sort of by teaching himself. And he eventually got a degree in mathematics. But sort of interestingly, it's like somebody that discovers something, they just do it all differently than everybody else. It's like some painter, from Mexico or something. Here in college, she just paints differently than some European painter. She just sort of taught herself how to paint, So he taught himself how to do mathematics, but he decided there was a better way of doing it than everybody else done. So, and he invented, I sort of first really got into it because I do a lot of work in array programming. Like we use NumPy, CUDA, and array programming. And he invented this language called APL, which was for array programming. And that's what he's sort of known for. And, at Tableau, we use the array programming because we use like column sorts. So we organize it down by columns, and then instead of having like SQL queries, you just think of this as each column as an array, and you're just doing operations on an array. So it's like, So this idea had come along by the APL community. Actually, they started working on databases where they thought of databases like columns, not as sets of records. And it turned out to be super useful for analytics. And I got tuned into this because Iverson's protege, a guy named Arthur Whitney, who actually lived in Palo Alto, he invented this language called K. And because I was looking at array programming, I met this guy and he explained it all to me. Anyway, so everybody knows about array programming, but that's not what Iverson's really known for. He's known for this APL notation. And if you ask him what his greatest accomplishment was this notation. So what he did was I'm sorry, but he was at Harvard, got his degree in mathematics. He went to work for IBM. He actually went to work for Fred Brooks. Everybody know Fred Brooks, right? VR, computer graphics, System 360. And this was in the 60s, and people really didn't know how to program computers. So he tells Iverson, go figure out how to program a computer. And we need some new ideas. Now they had Fortran and a few other things, but Fred Brooks said we need some new ways of doing it. So Iverson said, well, I'm just going to use my notation that I invented to program computers. And Fred Brooks and Iverson actually wrote a book together. It's called Data Processing Algorithms. It was Fred's major book. So just interesting. I talked about Fred. Fred's a big fan of likes all these kind of stuff, just like I do. But anyway, all right. Here's Iverson's notation. So this is written in K, not APL. But I think you can figure it out. So it's an array processing language. So if you say till K, that's like the Python range statement. You just enumerate a list of 5 elements in this case, or 4. Then after that you just start doing vector operations. So if you get 2 times K, you just multiply the element by 2. You add 1 to that, just add 1 to every element in the list. Okay, and then one of his inventions was this thing we call scan, now reduced, and he said plus slash, which he called the over operator. And that can you can have any operator on the left that you want, times if you want. But that just means put the plus between each of the elements in the list and then sum. Okay? So that's an operator. I over that gives you 25. So this language is a little weird. It doesn't have any precedence, and you sort of evaluate it from right to left. Notice that? And by the way, if I would have said 1 or 2 times 3 times or plus 7K, the 2 times 3 would not have precedence. You always just go in order from right to left. And he just didn't realize that precedence was a useful concept. I mean, he invented this himself. But anyways, but that's the way he did it. He said, and even nowadays people argue about precedence all the time. It's a very hard thing to teach people. Anyway, but there's this intriguing statement that these two things are the same. But another one of his big breakthroughs was he tried to prove things about his program. So he had this notation, and he used this notation, like imagine you're learning math in high school, and you just derive all these theorems and formulas and algorithms. And so he would do math in this notation. So this is a proof that sum is equal to K times K that he derived. So, you can sort of scan through it. What's 2 times K? Well, what's multiplication? It just means repeated addition. So you just add these 2 things together twice. Okay? If you did 3 times K, you add 3 of them. Then addition is commutative and associative, so you can reverse a list. That's allowed because it's commutative. Okay, then you can reassociate things. So if you reverse this list, you have these 2 lists, and then you can combine them and get 2 plus 2 plus 2. Okay, that's just because of commutativity, associativity, which still works in his notation. And then he had this operator repeat something, some number of times. So 3 numbers signed 2 means repeat 2 3 times. So make a list of 2's repeated 3 times and then sum it. So this thing is actually equal to K minus 1 repeated K times. And then if you add 1 to the list of K elements, you add 1 to each of the elements. So that's actually equivalent to K repeated K times. Okay? And then if you sum something repeated K times, that's the same as multiplication. So he just attempted to imagine this 10-year-old, writing this down and figuring this all out. So anyways, totally cool, right? So he was proving all these things. And I guess, this is really important because, it's what you can do with your notation that matters. It's like with your visualization, what can you do with it? So here you're doing proof. And not only that, you can do this proof. You know what I mean? Like you can argue whether this is a proof. But I think we all agree this is a proof. Now, this is a good way of sort of suggesting a proof, but not most people want to agree this is a proof through all K. Now, it's plausible that this can be generalized all K, but mathematically, the induction, you don't have induction. Okay, so anyway, he wrote these books. Like, he's famous for this APL. And he wrote all these grade school books. So he wrote a book on arithmetic. He wrote a book on algebra. He wrote a book on calculus, where he used this notation to rederive all this mathematics. And it's really fun to read it. Like, you sort of see some of the stuff in the algebra thing. And anyway, it's totally awesome. So anyways, check it out. Okay. So, but then his paper goes on like, what's a good notation? What's a good notation for things? And it's almost, I've reworded his points to make them more familiar to me as a visualization person. But these would be very similar things that we would argue for in a good visualization. So you should have a natural encoding. Right, like, we use that all the time. Like now, use space before you use colors. You should have meaningful patterns. Like, a lot of things are like idioms, like patterns on a table. Idiom that we all use. And in math, you have patterns like the distributive law. So the notation should reflect the meaningful patterns. And it should be concise. You can argue about that. APL people sometimes think it's too concise, but I think the general principle of emphasizing the important things and de-emphasizing the unimportant things is very fundamental. So maybe concise isn't the right word, but there's some less is more. Right? Simpler is better than complex, etc., etc. And concise means if you're doing a lot of manipulation of something, it has to be simple. Because you can't manipulate really complicated things. So you have to have concise notation. And then, of course, he wanted it to be formal. You don't always want notation to be super formal, but he wanted to sort of ends that mathematical system. So anyway, I thought that there are these principles that apply to things like notation that are very, very similar, I think, to principles. They're not one-to-one. There's obviously lots of complications and lots of maps versus math text, but I think the core principles, like I do this analysis. The core principles are what you want to find. Like what's common to these things. So I'm really interested in math notation. So this is a great book. It was written in like 1920 or something, 100 years ago. It's really the definitive history of mathematical notation. And it's really a cool book. Just check it out. It's like a tome, and it's really the only thing really written about it, that's scholarly. And the basic point of this book is, as people discovered more and more math, they invented notation that helped them do it. That's how we say it. So why do we have precedents? It's because they discovered, the distributed law. So that meant we had two operators times and plus, and it's easier to represent the distributed law if you just use less parentheses if you make multiplication of higher precedents. And why did we have exponents have higher precedents yet? Because they discovered polynomials. So you have ax squared plus bx plus c, and so you want that to be really concise, and there's no parentheses. So as they discovered these mathematical objects, they optimize their notation as they went. We take it for granted, but there's a process of doing that. And that process is very much like the process of discovering graphics, right? That you think of, Watt was making the first plots, he used instruments, and he'd have instruments, and the instruments would draw on paper, And so a lot of the plots were about weather and steam engines and things like that, because those were the instruments they had at the time. And so once they had those instruments, then they created those uniform visualizations. They didn't make plots before that, and bar charts and all these classic things that people invented. They're all reasonably recent inventions that evolve as we know more and more about the world and have access to different parts of it. So, anyways, but the sort of interesting thing about mathematical notation, I was thinking, is it's ambiguous and inconsistent and difficult to parse. I find this very ironic because all the mathematicians think they're so precise and everything's proved, but then they have this incredibly lousy, in some ways it's beautiful notation, but it's totally heuristic, And, a good paper on this is the paper by Wolfram a long time ago, where he described what it took for them to sort of parse and use mathematical notation in mathematics. And they have like 200 heuristics that they have to use to sort of ingest most math. And it's completely inconsistent, right? Like I wrote this book on rendering, and I think the whole thing I did was try to unify all the notation in the feed. One paper would use one notation, another paper would use another notation. There was no common notation, but when I wrote the book, I tried to make all the notation consistent. That was my contribution. All I did was make all the notation consistent. Everybody else had discovered it. So, but Iverson also didn't like it because it was declarative. He wanted something executable. So what's the deal with programming languages? So I like the programming languages. Well, they are pretty unambiguous. They're pretty consistent. They're fairly easy to parse, right? We designed them to be fairly easy to parse. They're executable, but they're not that expressive and not that extensible, not like that. So that's sort of interesting. So, one interesting thing I worked on off and on was a programming language where I could extend the notation. I called it Kajori. But lately, I've been using this programming language, Agda, and it had almost every idea that I could think of at the time and more. So, some of these modern programming languages, particularly ones that are sort of mathematical, have pretty elaborate support for introducing them. And another good example is the Eurovis. But anyway, one advantage is, you can use the entire Unicode character set, which, that's really nice because you have mathematical symbols in there, and all these other symbols for cultural symbols of all sorts of different types. And so you can just use those like one character. And so here's an example where you just define division operators in the division set. And, that. And, you can define new statement types and all sorts of stuff. So you can actually come up with something that looks a lot like and people have done other things, but just sort of interesting subject, which is, how do we create new notation in this thing. Okay, so the last thing I want to talk about, hopefully, I guess the point of that part of notation is a lot like visualizations, but it's somewhat different. It's easier to do. Last thing I want to comment on is back to that Eurovis talk. Is the key is to be able to use one or one of these at a time. Okay? And again, I'm going to use an example from Tableau. Okay? So actually, so there were three ideas in this system. One was, there was a famous paper called Query by Example, where what you could do is you could create a query for a database, and this was when I was a graduate. You could make a query by a database by trying to create a table, which was the answer we wanted to see. So you drag the fields into the columns of the table, and you would get a query and you make that table. It was a different approach to database queries than SQL kind of things. And then there were pivot tables and cross tables. So that's a way of interacting with these things that you use this Tableau. This is a paper. But the key thing was that we had this underlying notation in the language that unified queries and visualizations. Okay. So you had these two different representations, the visualization and the query. And in order to be useful, you had to be able to execute a query. You had to be able to get the data you needed, do computations you needed, etc. So, our visual language sort of looked like this. This is a little picture of it. Select as a circle, candidate cross longitude. So that was on the x-axis. You can see the two candidates. It's two candidates and two panes. and use this cross product thing to indicate that. And we have plots in time so you can form patterns and all that kind of stuff. And then you just sort of, augmented this thing with what this table drag and drop interface did. So you just copy what was on the interface into this language, and it's self-explanatory. I mean, I think that you can see sort of how that generates. Again, this was highly motivated by graphics and other things. But, if you look at it like this, it's not that hard to translate that into this, which is a query. And that, if you know SQL, that is a valid SQL query. And it's almost exactly the same thing. So what's sort of interesting is what you do is you have these two different things which you think are completely different, but because of the semantics and the notation, they start looking very similar. Now they're still different, in the visualization, some doesn't make sense. That's not a visualization concept. So it's still there. And in the visualization, there's all this semantics. Actually, there's semantics as well, but there's all this semantics here. Like, for example, we know how to encode party really efficiently. We know how to make axes. And we know that latitude, longitude are two coordinates. So we map in the background. And so we also have all the semantics. In fact, the semantics was the key. Because we could realize much of latitude geographical things, category and zip code, party, ordinal things, some things we quantitative. And we have a whole ontology that would guide us and help us map the notation and semantics, and so we can make much easier to understand pictures because we knew what, for these different semantic domains, what maybe a good representation of the image would be. So there's a bunch of semantics in there, but so that's not really present too much in the query, although there's stuff like that in the query too. Like we know that certain things are inherently part of semantics, what are independent variables and what are dependent variables, and what are functional dependency. So we know that aspect of that too. So we know what's independent, what's dependent, what's independent, what's factor. And so that's really important because if you know what's dependent on and you get more deceived. So there's a rich semantics you want to put in. And in fact, most of business intelligence is actually called semantic modeling. I didn't realize that when I started talking about the big players in there, the companies like Business Objects, what they do is semantic modeling. And so you just map the semantic modeling up to all your visualization and analytical stuff. And so it's all about the semantics. It's semantics, not visualization. Because once you know the semantics, then you can make a better visualization. So anyways, so you have this core of basic ideas. You look for the commonalities. Like you notice that the structure of Bertrand's graphics and the structure of dimensions and databases and categories and coordinates and so on were related. And so you use the same mathematical formulas and the same notation for those things. But then you augment it to add the other features you have. And so that's how you generate. You just combine two different views of something and find the common parts, and find the different parts, and try to make it seamless. That's my magic trick, so try that. It works pretty well. Okay, so really, I would argue it's semantics and syntax, that they both are really important. For the viz crowd, I'll argue for semantics. For the programming language crowd, I'll argue for syntax and notation. This thing about efficient things are really important. I do want to emphasize the point that you want to be able to manipulate things in semantically meaningful ways. It's not just about looking at the thing, it's what you can do to the thing. Most visualizations, you can't do anything to it. All you can do is look at it. You can rotate them maybe, okay? In fact, we used to monitor our interface and we'd say if people did any graphical stuff that we sort of love, we think that's bad. If they have to change the view, if they have to scroll, they have to do anything graphical, that's a change of color, that's bad. They wanted to do semantically meaningful databases. So anyways, you have to be able to do it. And then I think the really exciting area is relating different representations. So, I didn't talk about this too much, but LLMs are really good at translating from one language to another. They're really good at translating to programming languages. Great success translating natural language into SQL. Great success translating natural language into mathematical. And the DSL constrains it, prevents mistakes because it doesn't do grammar, encodes and laws. And so it tends to do a really good job. And then, with the multi-model embedding, we can embed these different representations in some vector space, and then they can sort of share semantics. So I think that's it.
Questions, please come up to the microphone and ask a question. We have, I guess, a few minutes for questions.
Must be something to do.
This is Scott from Stuttgart. It's really interesting. I was wondering, you talked about distributed cognition and cognitive costs. What do you think? Do you have some take on what are cost structures or costs that we're not understanding while you're doing visualization? What that mean each customer, that mean each customer?
Well, I think certainly the external versus internal. Like we don't always write, we don't really make it clear what the person has to do and what the visualization is doing for that, right? And so like a lot of people just don't even write that down. What's expected of the user, what's expected of the visualization. So I think figuring, like, or another way of saying is, like, what are you offering from the person? Usually it's just working memory, but there's a pattern finding. But let's write down, what you're trying to do to help the person kind of do it. Just write it down. And then, I think you have to think through the steps that they go through when doing various types of analysis. And then you have to do that for each customer. So, that gets harder to do because, especially if your system is somewhat smarter and hot, but if you watch them, they tend to be very repetitive. You just have to watch them and get some clues. So, this stuff, I think most of what I found is it's like norm, you get rid of all the really stupid things. You just sort of say, that's a really bad idea, because that's going to probably know that. And so once you know those things, and you get rid of all those bad, like most visualizations I see are terrible. I just look at them and say, why would you do that? So, it's like you just have to learn, it's like programming. Don't do this really stupid stuff. That's how you how to optimize it. So I think that's sort of where the state of the art is. But you get better at it. You just have to practice. And if you hang out with people that like to, deconstruct these things, like psychologists and so on, then Barbara will just explain it, to them and then other psychologists and they will talk about it. So you just have to it's just a sort of a skill that once you sort of realize it, once you have it, it becomes almost second nature. So if you show me a visualization, I can articulate why I think it's good. I can say it's not going to be good for this. It's probably going to be good for that. That's all I use. So that's how it is. But I found it works pretty well because if you just do the random thing, which most people do, it's usually terrible. Most visualizations are terrible. Yeah. You just don't help people.
Roy Ruddle, the University of Leeds in England. Thank you very much for telling me things I didn't know, but also making me think differently about things that I do know. Going back, or building on the idea of cost, and you gave this really nice example of tables versus a matrix of bar charts, and relating the visual search time, and hence cost, and explaining the way that we use that to convince people that visualization was useful. So you can imagine the conversation in a sales that goes, all right, yeah, everybody's going to use visualization. And then you tell the potential customer how much that visualization system is going to cost them each year.
In dollars.
In dollars, yeah. Which then takes you on to the idea of how much is that insight worth. And we're familiar with the idea of visualizations generate insights, but not all insights are equal in terms of benefit. Some of them are fairly trivial, some of them are absolutely profound. So, what techniques, what methods, what examples did you use to try to convince people of maybe the immense value of occasional insights coming from, let's say, a large amount of usage of the tool? Maybe it's not the cost of the tool, but it's the amount of time you spend doing that visualization.
But there's a couple of things in there. First of all, the insight one. Actually, I don't find that a very helpful way of thinking about it myself. I mean, not that people don't take insights, but 99% of what people do is like answer a question, some hypothesis or some, want to know something bad. It's like typing in Google, you're searching for information or something like that. You don't use Google to find insights. You usually have some more specific goal. So what I always would do, first thing I would do is like, what are you trying to, like what question do you want to answer to? Okay, and it's usually fairly specific because most of these people don't just like to play around with visualization systems. They have a full-time job, So they have some specific thing they want. And then what you do is you figure out, why can't they do that? And that's what you work on. Now, I think they do get insights as they go, and over time they do more doing stuff. But I think most systems are so bad that they just don't get anywhere. So if you just lower that first order barrier, you make a lot of progress. So I'm very pragmatic on it. I make it easier to do, and then if it's not capable of answering it, it's really easy for you. Like 90% of the time, they'll tell you they're trying to find out something. There's no way.
Yeah, so you're focusing on making it easier for them to find the answers to the questions that they know they have.
Yep.
And by the way, there'll be other things you find out along the way, which equate to the serendipitous.
Yeah, and then they develop skills and analytical techniques, say, or analysis. So they develop other stuff which lets them get to that next level. That's excellent. So that's always been my approach. I am a very pragmatic person, despite this talk. Okay, this is very pragmatic. I mean, just make it easier and faster. Like I said, how do we know one representation is better? It's faster and less expensive. Simple as that. You can get a lot of mileage on that. Then you get into comprehension. I still talk to all my psychologists friends about comprehension. I still don't quite get what that is. But then you get into insights, I have no idea what that is.
Great, thank you very much.
So, as a timekeeper, I have to ask you to thank Pat for